last time, and we kind of found out that there were no rational roots. So I kind of think maybe that's not the best approach. Sometimes, pre-calculus says, oh, we need to find the zeros, and even the list of things to do says find the zeros. But I think we found out here that it wasn't very efficient. So what we're going to do is we kind of have an idea of where it is, but let's say we start it all over again, and instead of trying to find the x-intercepts, let's find the points where we have maximum and minimums, and see if that information alone would allow us to know what to do in the first part. So let's take the function here. Okay, so we're just going to take the first and second derivative and find the zeros. So we take the first derivative of this, and we'll get 3x squared plus 24x minus 5. And the second derivative is 6x plus 24. So you can see setting the second derivative equal to 0 and solving for x, that comes out pretty easy. That's the easiest one. So x equals -4. So that is a possible point of inflection, but we don't know yet until we check the second derivative on either side of it. This one, there might be a way of grouping that, but let's just use the quadratic formula. So you get -24 plus or minus the square root of minus b plus or minus square root of b squared minus 4ac over 2a. Okay, so let's see what we get with there. 24 squared minus 4 times 3 times -5. And you get -24 plus or minus the square root of 636 divided by 6. Okay, so what's the square root of 636? 25. Okay, so we get -24 plus or minus 25.2 divided by 6. One thing you'll notice is when you do use the quadratic formula, this number here is -4, which equals that number there, which is -4. That's not a surprise. Well, it's not a coincidence. So the maximums and minimums are, I wouldn't say always, but so I don't want to generalize that, but most of the time they're centered symmetrically around the point of inflection for a third order polynomial. So the center of this, you're plus or minus 25.4, but it's centered around -4. Just want to make sure so let's get the decimal equivalents here. -24 plus 25.2 divided by 6 is approximately 3. So if you take the positive square root, something's wrong there. Oh, I raised it to the 6th power, not divided by, something's wrong. Okay, divide by 6. Okay, so you're going to have 0.2 and take the negative. So -24 minus the square root, not the square root, minus 25.2 divided by 6 is -8.2. Okay, so those are the those are the critical numbers, which are possible minimums and maximums. So what we do differently for these curve sketching problems is we make up a table, but it's kind of oriented 90 degrees. So let me fill in what we have. You have interval, but instead of the interval going this way, the intervals are going to go down that way. Then we have x, and then we have f prime of x, f double prime of x. So we put the first and second derivative information and then some comments over here in the last column. So the interval, in this case, we combine everything. So we want to cover the entire domain. So you're going to start from negative infinity, and then you go to the first number of the three here, which is going to be negative 8.2. And then you actually include 8.2. So we on negative 8.2. And then we have from negative 8.2 to the next number, which is negative 4. I don't know why I put a parenthesis there. Let me get rid of that. Or maybe it wasn't a parenthesis. No, it wasn't. So then it's negative 4. Then you have a negative 4. And then you go from negative 4 to positive 0.2. You put in 0.2. And then you go from 0.2 to positive infinity. So it's got a lot more intervals. So it includes the points, the actual x values, where the first derivative is either undefined or 0, and where the second derivative is either undefined or 0, plus the intervals between those points. So we already have some of this to fill in because we know what the x value was where, well, actually, this is not x. This should be f of x, sorry. So this is the value of the function. So we could plug in these three values into the function and find out what the values of the function are at the two critical numbers and the point of inflection. So let's do that. So we have to find our original function. So we're going to do f of negative 8.2. We're going to do f of negative 4. And we're going to do f of 0.2. And so that's going to be negative 8.2 cubed plus 12 times negative 8.2 squared minus 5 times negative 8.2 plus 20. And the next one would be negative 4 cubed plus 12 times negative 4 squared minus 5 times negative 4 plus 20. And the final one is 0.2 cubed plus 12 times 0.2 squared minus 5 times 0.2 plus 20. Okay, so we need to figure out what those are. So go ahead and get your calculator out just to make sure you know how to do this right. Because one thing is when you do negative 8.2 cubed or any of these negative cubed, you've got to make sure that you put the negative in parentheses. So it's going to be you'll use the left parenthesis negative 8.2, then raise that to the third power. If you don't put it in parentheses, it actually works out okay on this. It actually, if you do it for the squared, it'll give you the wrong number. So, but just not as a matter of procedure, you probably want to put those numbers like they're shown in parentheses, just to make sure that you're you're doing the proper. And you can also go back and then just change the numbers inside the parentheses. You don't have to rewrite the whole equation. So that's another nice thing. Okay, make sure I did that right, since I'm telling you to do it the right way. Okay, so you check me out here, 316.5. Okay, next one I get was a 168. Stop me as soon as you realize I've done something wrong. If I've done anything wrong. And then I get 19.5. Okay, so those are the values of the function. So we'll plug those into our table. So we've got 316.5, 168, and 19.5. Which you notice they're all on the above the x-axis. That's why we didn't end up with very many x-intercepts, because these are all above the x-axis. Okay, the next thing you're going to do is you go to the next column, which is the derivative. So the first derivative was 0 at these 2 points, and the second derivative was 0 at that point. So if they were undefined, you'd write UND for undefined, or you could write undefined. So they're either going to be 0 or undefined. For polynomials, they're always 0. And then the final thing you have to do is you have to fill in these empty spaces with whether it's plus or minus. Now, when you have 3 of them right next to each other, you really only need to find out the value or the sign in one of them. And then because the concavity only changes here, if you find it anywhere in this interval from -4 to infinity, then you can fill them all in with positive. So it's not like you have to do however many blanks there are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You really only have to do 1, 2, 3, 4, 5, because there's 5 continuous areas. So again, you can just pick values of x, which are in the different intervals, and look at the first and second derivatives. So we need the equations for the first and second derivatives. Let's move those over to the next page. And okay, so let me erase that a little bit right there. Okay, so those are the equations. So if we do f, let's do f prime first. So we can do f prime of negative, let's say 10. So that's in this interval. I figured 10 was easier than 9 because it's, so you get negative 10 squared, 3 times negative 10 squared plus 24 times negative 10 minus 5. So that's going to be 3 times 100 minus 240 minus 5, which is going to be positive. Okay, I just did it far enough till I could figure out whether it's positive or negative. I don't really care what the value is. So this is positive. Okay. The next one, I'd probably choose 0, because you can see in this interval, which is from negative 8.2 to 0.2, the easiest one to evaluate is 0. So that's going to be negative 5. So that's equal to negative, so that goes there. And that makes all of these negative. And then finally, I could do f prime of 1, which is in this interval. That'd be the easiest thing to do. So you have 3 times 1 squared plus 24 times 1 minus 5. And you can see, since this is negative 5 and these are all positive, it's going to be positive. So this is positive, which is what we expected. Okay. And then here we have to just do it in 2 places. So f double prime of 0, that would be inside this interval from negative 4 to positive infinity. You can see f double prime of 0 is going to be 24. So that's positive. So these are all going to be positive. And then I could do, if I did f double prime of anything less than negative 4, so I'm going to do negative 10 again. So you do 6 times negative 10 plus 24, which is negative 36, I guess, which is negative. That goes in here. And now you have your table filled out. So it's not as daunting as, what happened there? It's not as daunting as you may originally think if you use some okay. Now, as far as the comments, it's the same comments that we made when we used the first and second derivative test. So all you have to do is look at the signs. The other thing you can do is you can either use the first derivative test or the second derivative test to figure out whether these are maximums or minimums or whether they're points of inflection. So at places you have 0, you would make some comment about minimum or maximum or point of inflection. These other places you would just say increasing concave up. This would be decreasing concave down. So let's do the first ones, which are the critical numbers. And so these critical numbers, this is concave up. So this tells you it looks like that, which means that it's a minimum. Up here, it's negative, which means it's concave down, which means that it's a maximum. And then here, where it's 0, we go from concave down to concave up, so we have a change in concavity. So this is a point of inflection from that information. So again, we use the second derivative test here to figure out whether this is a minimum or maximum. Second derivative test, or we could have used the first derivative test, increasing to decreasing, same thing. And then in the other places, you would just put increasing, I'm just going to use abbreviations, increasing concave down, that's CDs for concave down. Here you'd have decreasing concave down. Here you would have decreasing concave up, and here you would have increasing concave up. So those are the other comments. If I had more space, I'd write them out, but I don't have enough space. So that's the basic concept of using calculus to help you. Well, we haven't drawn anything yet, but with all that information, we should be able to draw a pretty good curve. So let's do that, and this should help us figure out what the x-intercept was. So what I'm going to do is I'm going to add a page here, put a piece of graph paper in it. Put a piece of graph paper in it. That's not graph. Okay, so this leads me to another little thing here. So here we were looking. Well, okay, so we're having a retaining wall rebuilt. So a retaining wall is just a wall to keep earth from falling down. So we have a driveway, and then our neighbor's house is further down. So we have this wall built up, and there's fill, and then the driveway on top. And it was starting to look like this. So at some point it was going to go like this and look like that, and then so we decided to have it rebuilt before it went. So since we were having to stick around the house while the guys worked on that, Martha said, well, she kind of alluded to this. Hey, let's go into the attic, which means usually cleaning stuff out. Okay, so we had to clean stuff out. And I had 2 remaining boxes of old notes in my attic. So that's what this is, which I'll talk about in just a second. But that leads me to the second point. There's an article in the New York Times on Friday called, it was about elderly people. Hopefully I'm not considered elderly yet, but I'm getting in that direction. Okay, so in Sweden, they have this cultural thing where when you get to a certain age, you start throwing stuff out instead of leaving all that stuff to your children and grandchildren to have to go through when you die. Okay, so they call it death cleaning or something like that, which sounds kind of morbid, but that's what it is. It's basically cleaning out your house of junk that you know your kids are never going to want and you haven't used for 40 years. So this was our death cleaning. So we don't have too much. The only thing we have left in the attic is some stuff that is actually our children's stuff, not our stuff. They've left for us as they've moved to smaller places over the years. Okay, so anyway, I have this book. It's ME 3031, which was thermodynamics and instrumentation. These are junior level classes, and there's also there apparently is one on labs, which that was what I did really poorly on. But in the description of, this is for lab reports. So here's the page on significant figures. So this is all these things. Often it is necessary to make calculations based on measured quantities. Anyway, they talk about, a number of significant figures. We know all that about that in physics. The second one is rules for curve plotting, which is kind of irrelevant. It's kind of relevant today. So this was, so here's some of the rules. Draw in a pair of axes indented sufficiently from the edge of the engraving to allow for numbered and labeling of the scales without entering the margins. That just means make your graph small enough so you can put labels. Each axis must be labeled in the proper units given. Blah, 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 blah. The independent variable is always plotted along the x-axis and the dependent variable on the y-axis. Choose convenient scale factors for each of the scales, always using multiples of 2 or 5. Scales whose subdivisions amount to 2.5 or 3.33 are very troublesome. Okay, so that's what we're doing right now, is we have to choose the scales for the axis, and they're not going to be the same. So if you look at what we have here, the most exciting stuff is happening, between negative 8 and positive 0.2, but we're going to make it larger, and we're going to make the scale go from negative 20 to positive 20. That's so that each increment here is 2 units. So I followed the rules. Okay, so this would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, the same way over here. Now in the other direction, you can see I've got some pretty big numbers, so I'd want at least 300 and something. So I'm going to make 400, and I think that is no, that's not a multiple. Let's see. So 400, yeah, so if I do positive 400 here and negative 400, then it would be 40, 80, 120, 160, 200. So this would be like 200. And this would be negative 200. So you have to choose the scales. Now, if you were doing it using a graphing program, you might zoom out. But even so, if you zoomed out, you might want to use those kind of. I would probably still use those kind of rules. Okay. The plotted data points should be clearly marked by drawing a small circle around each point. These should be drawn with a template for neatness and should not be more than 3/32 inch in diameter. So that's kind of interesting. So you used to have these circle templates. So you'd have a piece of plastic and there would be circles of different sizes, and you'd use those to draw the circles that you would do to represent where your data points were. I don't have my circle template anymore. If points for more than one curve are to be placed on the sheet or the data of different observers is to be indicated, a differentiation can be made by using small squares, triangles, or other symbols in addition to circles. You can do that in Excel. You can change what the data points are represented by, but back in the old days you actually had to do that yourself. The best smooth curve is to be fared with a French curve, not freehand, through the data points. So I showed you what a French curve was, right? Remember that? Yeah. So here's written proof that I didn't make that up. It is not necessary that the curve intersect all data points, or even the first and last data points. It should, however, be a smooth curve, which best represents the data. Okay. I don't have any French curves, so I'm going to do this by hand. So that's, but so let's put these data points in here. So you have negative 8.2. So we're going to go 1. This is 2, 4, 6, 8. This is 10. So 8.2 is about right here. And then 316. So we're going to go up here, 200, 240, 280, 320. So it's going to be about right there. Okay, so that's this point. The next point is negative 4, which is right here, and 168. So this would be 160, so 168 is about right there. And final one is 0.2, 19.5. So 0.2 is really close. 19.5, that's 20, right? No, it's not 20. That's 40. 40, 60, 40, 80. Yeah, okay. So let me go down a little bit. So 0.2, 19.5. That's about right there. Okay, so we have those 3 points. It looks almost like a straight line, but what we do is we know that this has to be a maximum. So I'm going to draw the curve so that it has a maximum here. We said it's a maximum because its first derivative was 0, or it went from increasing to decreasing. And since the curve is going to be kind of symmetric, to make this thing actually fit through here, it probably has to have a shape similar to that. And then it comes down like this, and then it's going to curve back up because this is a minimum. And then again, it's going to be reasonably symmetric, and then we kind of draw it up like that. And the same thing applies down here. So if I bring this down, so these are reasonably symmetric. They're not exactly symmetric, but they're pretty symmetric. So that with just those 3 points, because I know one's a maximum, one's a minimum, and this other one's changes concavity, I come up with it now tells me that I only have one x-intercept, because the minimum is right here, so it can't go any lower. And it also shows me that the x-intercept is around negative 16 or 15, which is what we found out kind of earlier. We weren't really able to track it down exactly, but we went through all this trouble, when we were doing all this stuff using guessing, and that's all it is, guessing at what the intercepts are, finding out the x value. We were able to see that somewhere between negative 10 and negative 20 that it went through 0, probably closer to negative 10 than negative 20. So, the next step, and we also found out that y-intercept was somewhere back here. That was easy. The y-intercept was 20, which kind of agrees with what we saw. If you see the curve, you see the y-intercept is about 20. It's about halfway, because the minimum was 19.5, so it has to be greater than 20, since that's a minimum. So the only thing that we really have left to do, we have the y-intercept, we have the relative maximum, the relative minimum, the point of inflection. It would be to find this value of x to maybe a better accuracy. And we'll learn how to do that in another section. So the only way that we could figure this out is right now is just probably guessing numbers. We could use our calculator. It would do it for us, but that's not the point. We could try negative 15, plug it into the function. Try negative 16, plug into the function. If it changes sign, then there's a zero. There's a zero in between those two. Okay. Okay, we just did all that stuff. We just did that too. To organize the plotting of the graph, you want to create a table with the following information: critical numbers, where the second derivative equals 0, actually where both of these are also undefined, the vertical asymptotes, which is actually where the second derivative equals 0, and the intervals between all these. Add the critical numbers, calculate the value of the function and the sign of the second derivative. Okay, we didn't do that, but we could have done that. and at the x values where f double prime equals 0, calculate the value of the function. We did that. At all points and in all intervals, determine the sign of first and second derivatives. So we did that as well. So that's kind of that's the procedure that we just did. So we could do another polynomial now, but I want to do another kind of function just to kind of demonstrate the process. Actually, what I'm going to do here is, well, if you go in your book, and I'm going to work this problem out, but I'm going to do it separately. In this particular section, section 3.6, they give you different examples, rational functions, trig functions, and they show the original function. They show the first derivative. They don't tell you how to get the first derivative, but it's just using the quotient rule in this case. The second derivative, again using the quotient rule. The x-intercepts, the y-intercepts, all these things that we talked about, where the vertical asymptotes are. Then they create a table and fill it in like we just did. And then based upon the table, they're able to make these conclusions. And then you draw the graph. So if you read your book, that's kind of what they leave a lot of stuff out. They don't show you how to get the vertical asymptotes. They don't show you how to get the x-intercepts. They assume that you know how to do it. But it's been a while since you've done it, so we'll go through this one, and we will go back and work through every step, since they leave out every step because you guys are not experts at pre-calculus because you've not done it for a year. Some of you never were experts at pre-calculus. Some of you were. Okay. So this is a different kind of function, but it demonstrates the procedure. So let's we'll hide that, come back and check it out. Okay, so we have a rational function. So what we need to do is we need to take the first derivative, find the values of the first derivative where find the values of x where the first derivative is 0 or undefined. Take the second derivative, same thing. We can make up a table from that and completely populate the table. We also need to find the x and y intercepts if they're vertical and horizontal asymptotes as well. So let's start off by doing the derivative. So, and actually I'm going to, because we're using the quotient rule, I'm going to change that to h. So we can call one part f of x and one part g of x. So f of x would be equal to 2 times x squared minus 9, and g of x would be equal to x squared minus 4. So we take the first derivative here, and we get 2 times this derivative of this, which would be 2x. So that's 4x. And the first derivative here is going to be 2x. So the quotient rule says h prime of x equals f prime of x times g of x minus f of x times g prime of x, all divided by g of x squared. So we just have to simplify the numerator. So we're going to multiply it all out. So we'll get 4x cubed minus 16x squared minus, okay, we got 2 times 1 times 2, so that's 4, minus 4x cubed. So we got 2x squared times 2x, which is 4x cubed, negative sign. Then the second part is going to be negative times the negative, so that's going to be positive. And you're going to have 2 times 9 times 2, which is 36. And it's going to be 36x. So that's multiplying this out. It's all divided by x squared minus 4 squared. These cancel out. So what I'm left with is negative 16x squared plus 36x divided by x squared minus 4 squared. Let's see what they had on the previous page. What did I do wrong? Yeah.
This 16x squared should just be 16x.
Oh, this one here?
Yeah.
Okay. Yes, you're right. Thank you. So that should just be 16x. That's why then it works out. Okay. So 36 minus 16 is 20. So I get 20x. Now that matches up. 20x over x squared minus 4 squared. Okay, good. Okay, the next thing we do is to take the second derivative. So h double prime of x is something. So again, we'll call this f of x just to call it something. So f of x equals 20x. G of x equals x squared minus 4 squared. And so f prime of x equals 20. And g prime of x is going to be equal to x squared minus 4. Okay, so that's the argument. The exponent is 2, so I take that down. And then I take the derivative of what's inside, which is 2x. So I'm using the chain rule. Or I could multiply it out and then just use the regular way. So if I multiply this out, I'll get 2x squared times 2x, which will be 4x cubed. And the second part is 2 times negative 4, which is negative 8. Negative 8 times 2x is negative 16x. You can see that if I multiply this out, I get x to the 4th minus 8x squared plus 16. If I take the derivative of that, I'll get 4x cubed minus 16x. So that was just a check to make sure I did it right. Okay, so then finally, the second derivative is, so h double prime of x is going to be 20 times x squared minus 4 squared minus 20x times, and actually it's better to keep it in this form, the factored form already. So I'm going to take 2 times 2x, which will be 4x, times x squared minus 4 all over x squared minus 4 squared squared. So this is f prime of x times g of x minus f of x times g prime of x. Where what I've done here is I've combined these two into 4x. And the reason it's better to leave that, as you can see, I've got this common factor, x squared minus 4. So I can simplify that. I can cancel out x squared minus 4. So you lose one of those, so you get 20 times x squared minus 4 to the first power. Here it cancels that out completely, so I get 20x times 4x over, and instead of this being to the 4th power, so something squared is to the 4th power, you get x squared minus 4 cubed. And finally, if we clean it up a little bit here, we'll multiply out the numerator, so you get 20x squared minus 80 minus 80x squared. 20 times 4 is 80. X times x is x squared, all divided by x squared minus 4 cubed. And 20 minus 80 is negative 60, so we get negative 60x squared minus 80 divided by x squared minus 4 cubed. And if you factor out negative 20, you get negative 20 times 3x squared minus 4 plus 4 divided by x squared minus 4 cubed, which is what they have. So that's, they left a lot of stuff out. But one interesting thing here is with the rational function, it always happens this way. If the first derivative is x squared minus 4 squared, then the third derivative is always going to be x squared minus 4 cubed, because you'll always end up with this factor. There'll always be this in each one of the terms in the numerator, which you can cancel one of those out. So it ends up being third order. So if you took the derivative of this, it would be, so the third derivative would be x squared minus 4 to the fourth power. But you can see that if I squared this, I actually get to the sixth power. So there's going to be x minus 4 squared in each one of the terms in the numerator. So you can always, that's why it's best to not multiply it out, which I did, but it's better to leave it in this form, because this is always going to be canceled out by one of these terms, or at least one. The next one is going to be 2. Okay, so that's how they got these things. That's how they got the first and second derivatives. So now that we have that, we can make up, well, we've got to figure out when those are 0. So let me rewrite them again here. So f prime of x equals 20x divided by x squared minus 4 squared, and f double prime of x is negative 20 times 3x squared plus 4x divided by x squared minus 4 cubed. Okay, the question is, when does this equal 0, and when does that equal 0? So this is something you guys should be able to answer. So let's see who I'm going to ask here. We'll ask the homecoming queen. So the first one, what values of x is f prime of x equal to 0? Not the denominator, but the numerator. When is the numerator 0? For what values of x?
0.
Right. Yeah. A lot of times people keep thinking they've got to look at the denominator, but the first derivative is undefined at 2 and negative 2. If you if you factored that. So you always just look at the numerator for zeros, whether it's zeros of the initial rational function, or if it's zeros of the first derivative or second derivative. So the only values of x where the first derivative is equal to 0 is where 20x equals 0, which is when x equals 0. So it's easier than you think. Okay, so f double prime, or f prime of x equals 0 when x equals 0. Okay. So, Zane. So what values of x is the numerator going to be 0? Yeah. You don't know, or you don't think there are any? Because if you think about it, if you set 3x squared plus 4 equal to 0, and you tried to solve for x, you'd end up with, so let's just do that. All we're going to do is we're going to set the numerator equal to 0, and this part is just a factor, so that's not going to affect anything. So if I said, when is this true? Well, you'd subtract 4 from both sides, and you divide by 3, so you get negative 4/3, and then you say, okay, I'm going to take the square root. What's the problem? Can't take the square root of a negative number, right? So the answer is equals 0, never. Okay, so there are no places where the second derivative is equal to 0. The second case is, are there places where the second derivative, we get too used to just doing the 0. So also f double prime, or f prime of x does not exist at what, and f double prime of x does not exist at, there's two values of x, which are, who am I going to ask here? Daniel. Yeah, right. Yeah. So it's the same values of x where the function does not exist. So the function does not exist at where the denominator goes to 0. So if you factor the denominator of the original function, or if you factor these, you'll still end up with, x minus 2 and x plus 2. So those are the values of x where the derivative is, first and second derivatives do not exist. Okay. So we have three numbers that we have to break the interval up into: 0, negative 2, 0, and positive 2. So let's see how many we need. We need a row for the header. We need one for the first interval to here. We need one to here. We need, let's see, header from negative infinity to here, from 4, this value, then from negative 2 to 0, then 4, 0, then from 0 to 2, and then 2, and then from 2 to positive infinity. So I think I got 8. Hopefully I counted right there. So I need 8 rows, and then I need one for the interval, one for the value of the function, one for the sign of the first derivative, one for the sign of the second derivative, and one for comments. So there's my table. So we fill this in. So this column is the interval. This is the value of the function. This is the sign of the first derivative. This is the sign of the second derivative. This is our comment column. Our first interval is from negative infinity to the first value of x where the function and the derivatives are undefined. Then we have the value of x where it's undefined. Then we go from negative 2 to 0. 0 is where we have a critical number. Then we go from 0 to positive 2. Then we have the x value where it's undefined. And then we go from 2 to positive infinity. So those are the intervals. And so what do we know so far? We know that the first derivative is 0 here, and we know that the first and second derivatives are undefined, as well as the function is undefined at negative 2 and positive 2. We also know there's a vertical asymptote. This is a vertical asymptote because vertical asymptotes are where the denominator is equal to 0 in the original function. That's why it's undefined. So that's what we know so far. And we need to evaluate the function at 0. So let's see what we get. So we're going to do f of 0. So the original function is this. If you plug 0 in, you'll get 2 times 0 squared minus 9 divided by 0 squared minus 4. So that's 9/4, 9/2. So if you plug 0, f of 0 is 9/2. Tablet's being a little weird here. Okay, back to business. So this is 9/2. Okay, now the next thing we have to do is just figure out what the signs of these, the derivatives. So this was 9/2. So we need to find out what is f prime of some value between 0 and negative 2. So I'm going to pick negative 1. Also f prime of 1. That's in this interval. we can also then do the second derivative. So we could do f double prime of 0. That would give us this, which would be the same for those two. And then we also need to find f double prime of, say, -3 and f double prime of +3. Those are these parts. Well, this one's easy. F double prime is 0. If we put 0 in here, we'll end up with, what will we end up with? F double prime is 0. You'll get -20 times 4 divided by -4 cubed. Okay, let's try that. -20 times 4 divided by -4 cubed. And I get 1.25. 1.25, that's positive, 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 positive. And then I have to do the other ones. So again, we're only worried about the sign. If you look at the first derivative, this is always going to be positive because you're squaring something. So all we have to do is look at the numerator. So if you put -1 in the numerator, it's going to be -20 divided by a positive number. So this is going to be negative. Likewise, if you plug in +1, the numerator is going to be positive. The denominator is always positive. So this is positive. So we can put a positive negative right here, positive right there. Actually, we'd still need to evaluate f prime of 3, I guess, and f prime of -3. But you can see the same reasoning applies. When I put in -3, I'm going to get a negative numerator. So this is going to stay negative, and likewise, this one's going to be positive. So you don't need to figure out the exact value. You just have to figure out the sign. Now here it's a little more, this part's always going to be positive because you've got 3x squared. That's going to be positive plus 4, so positive plus positive. So you're going to have a negative here, and the question is, if this is a negative number, then you're going to take the cube root of a negative number. But if you think about this, -3 squared is going to be 9. 9 minus 4 is 5, which is positive. So this is positive. If this is positive, then, and this is positive, then we get a negative in through there. So that's a negative. And the same thing, if you square 3, you're going to have 9 minus 5, 4, which is 5. 5 cubed is positive. This is positive. So this is going to be negative too. So these are both negative. Again, I didn't plug it into, you could plug it into the equation, but you can sometimes use some reasoning to figure out whether that's the case. And what we'll do here is we'll just check to make sure I did it right here. So we're gonna put the answer, see if I agree with everything that's in their table. So negative, negative, yep, undefined. Negative, positive, 0, positive, 9 halves, positive, positive, undefined, negative. So look at that. I'm amazing. No. So for the last 3 minutes, I'm just going to explain what I just did, just in case people got lost. So what we did is we took the original function. We used the quotient rule to find the first derivative. We simplified the numerator. We said what values of x does the first derivative equal 0? You only have to look at the numerator for rational functions to find zeros. So the only value of x where this goes to 0 is 0. That gave us that thing right there. We took the second derivative by using the quotient rule again. We were able to simplify it down to this. Because this is always positive, there's no 0. There are no values of x where the second derivative goes to 0. So we didn't have any cases where we could put a 0 in this column. But there were the cases where the first derivative, and the second derivative were undefined, and those are all occur where the denominator goes to 0, but the numerator doesn't go to 0. So we factored the denominator, x plus 2, x minus 2. It said that at those values we have vertical asymptotes, and also all these things are undefined. So we created our table based upon that information, and then we picked values of x in these intervals to check whether the first derivative was positive or negative, and whether the second derivative was positive or negative. And I ultimately didn't actually do the calculations. All I care about to fill out the table is whether they're positive or negative. So you can go to all the trouble of plugging them in and finding the exact value, but you don't have to go that far. You can look at just, if you have something squared, it's always positive. Those kinds of things sometimes allow you to answer the question without getting the actual value. So now the last thing we're going to do is just fill in the comments. So here we have we have decreasing because the first derivative is negative, and we have concave down because the second derivative. Here we have vertical asymptote. Here we have decreasing, and we have concave up. This is a minimum or maximum. Well, the second derivative is positive, so that's going to be a minimum. Also because we go from decreasing to increasing. Here the function is increasing, and it's concave up. And then we have increasing function concave down based on the signs of the first and second derivative. So the only thing we have to do is figure out we've figured out vertical asymptotes. We need to figure out the y-intercept, which we have actually done that, but we haven't done it explicitly. We haven't done the x-intercepts, but that's just setting the original function numerator equal to 0 and solving for it. The horizontal asymptote we haven't done, and we filled out the table, so we've got all the other information. So we'll finish this up next time, but I'm not going to assign any homework yet for this section. We'll do that next time.